Hey everyone, this is Mike Morris, Chief Technology Officer at Root9B. Thank you for joining the webinar where we're going to talk about the malware analysis of the advanced point-of-sale malware campaign that Root9B has been able to identify and be able to pull apart. The campaign is focused on harvesting payment card information for exfiltration. Root9B's malware analysis has determined that the adversaries use advanced memory resonant techniques to maintain persistence and avoid detection. This ongoing campaign has targeted numerous organizations and their point-of-sale systems. Root9B has been able to deconstruct the four major components of the attacker's activities, which we'll talk about in length here over the next half hour. So the webinar is going to be specific to providing technical analysis of the initial access methods, the command and control methods, and the newly identified ShellTea implant and PoSlurp POS RAM scraper. The four major components that we've been able to identify will be laid out by Matt Week, but specifically what you have is you have the initial access method where an end user is targeted with a spear phishing email. The recipient opens the active MIME Word document and clicks to enable content. Once that enable content is clicked, then what happens is the Windows machine will execute a PowerShell command to download shellcode. Once that happens, the shellcode blob comes back with a dynamic link library where malware is dropped in the system registry and loaded into memory, providing the attacker with initial access. We've been able to identify that initial dropper is a variant of Sniff, previously reported by both Trend Micro and Palo Alto. After the initial access, the attacker installs a second fileless implant into another registry shellcode blob. This specific one is the ShellTea implant, which Matt Weeks will talk about in depth. Finally, the fourth stage is the attackers will maneuver to the point-of-sale system. Once they get into the point-of-sale systems, they will deploy PoSlurp, which is a RAM scraping capability which will inject directly into memory of specific processes and monitor for a set period of minutes as defined by the attacker. So with that high level being complete now, I'll hand it over to Matt Week, who will walk through a slide presentation and talk about the specifics of the malware.
Thank you very much, Mike. With that, we'll go ahead and get started with our slides. As Mike mentioned, my name is Matt Weeks. I'm Root9B's Senior Research and Development Engineer, or Scientist, and I did a lot of the technical work here in the reverse engineering of the malware that we found in this campaign. So let's start with our ShellTea+PoSlurp campaign. So first of all, I want to talk about a little bit about the background, what happened prior to this point, what has this actor been doing before, what other malware related to these have been seen before, talk a little bit about the things, start off by going through the intrusion process, looking at the artifacts that we found here, which are variants of things, malicious pieces of code and malicious files that are known that they use for initial access, the macros specifically and how they launched PowerShell through WMI, and then the Sniff and PowerSniff malware that was used there. And then we'll start to talk about what they deployed after that point, which is the newer malware which they took advantage of. So to start off, we'll talk a little bit about some of the history of this actor. The most well-known malware family, which is indicative of this actor, has been called Sniff. Sniff has been analyzed publicly by a number of different security companies and independent researchers in the past. There's been a lot of good documentation lately, especially in 2015 and 2016. There is the group behind the Malware Don't Need Coffee blog has done a lot of reporting on that, and they posted some updates in 2015 about Sniff going to Sniff, which is originally a file-based malware, going to a fileless variant, or a variant which could load itself into memory delivered by an exploit pack. Trend Micro did an analysis of a piece of software in 2015, which they published. Proofpoint, Proofpoint did one in September 2016. And a couple of other companies have traced back the lineage. G-Data claims that they can trace variants of Sniff all the way back to 2007. So this actor has been around for a long time, slowly refining their tools. Dell SecureWorks, they like to call Sniff, which they also call ISFB, and occasionally some of the lesser-known names you might hear are Papras and Voslik. And they believe that that was originally designed for an early variant of Gauzy, which was a different piece of malware, which they can trace back all the way to 2006. And so this is a cyber criminal which has, or cyber criminal group which has been around for a long time and has continued to refine tactics as needed. Some of the old variants, especially the executables, which have been found in the past, do have detections by a lot of commercial antivirus companies. But again, that's only the ones that they know about. So you can write signatures for the malware which you've seen so far. But what we see with this particular actor is that they continue to add obfuscation and they continue to add changes in their TTP that will allow them to evade those detections from antivirus software and other security software. One important thing to note is that a few years ago, the source code to one of these variants, it was a Gauzy variant, was published publicly, and so that was leaked, or somebody who had access to it did publish it. And so one of the things that we find throughout these malware families is that when source code to one particular piece of malicious software is released, other actors will incorporate that into their toolkit, and we'll see the PoSlurp and ShellTea have incorporated bits of code which came from other malware families which have gotten leaked. And so sometimes you'll see a particular piece of malware which will have pieces in it which will have come from other malware families and other variants of the same malware. And so that is important to know and to realize. But if we could summarize this activity, this is a known actor which has been active for a long time and has been primarily focused on attacks against point-of-sale systems. They also do use some other malware, occasionally like Dridex, which is known for stealing credentials. And so sometimes you will see other malware families that were incorporated into the same intrusions. And so if we take a look at this, going from this background of Gauzy and Sniff, what we found is that the actor has moved to more of a focus on macros as an initial access method. And so macros are, of course, a way of automating Microsoft Office documents. Macros also have the ability to run any code, to go reach beyond the document and automate things, other things that are on a user's system. So it enables them to run malicious code simply by the virtue of the fact that macros are such a powerful programming language for Microsoft Office documents. So the access method which we saw them use was to use an active memory Office document. So this is a little bit different format than a normal .doc standard Word document. The structure of the document which is being sent is actually an MHT structure, which is a combined HTML format. It's not a binary format like the Word docs that normally end in .doc have. But if it's renamed .doc, when you double-click it, it will open in Office because Office will be set up, Microsoft Word will be set up to open files ending in .doc. Then Microsoft Word is going to read the contents of the file and say, oh, well, this is really an MHT file, but that's okay, I know how to open them as well. And so then it will go parse through that, which is a combined web page format. So basically, it can incorporate a HTML page, which is the main web page, as well as any embedded objects like pictures or scripts, or in this case, what they'll embed is a file of type application XMSO, and that stands for Microsoft Office, which means there is an embedded Office object within this MHT file, which has been named .doc. And the reason they do this, well, there are a variety of reasons, but one of the biggest ones is to evade detection of malicious macros from scripts and tools and intrusion detection systems which know how to parse the standard .doc format, but they don't know how to parse an MHT. So this enables the attackers to embed something which is a binary blob which matches the format of a doc with this embedded object, but place it into a container that can then evade some detections. And so within this HTML structure, there is this embedded Microsoft object, and that embedded Microsoft object is a binary object which has a macro in it. And so when the user opens this, it opens and it looks just like a normal Word document with a macro in it. Now, in a default install of recent versions of Microsoft Office, when you download a document or you open it from an email, that document will open in what's called protected view. And so you can recognize protected view. I'm sure many people have seen this before by the yellow bar on the top with a little informational shield there, which says, be careful, unless you need to edit, it's safer to stay in protected view, and then they have that button there for enable editing. Now, protected view blocks a lot of functionality of a particular Office document, such as editing, and so frequently users will need to go ahead and click that enable editing button in order to see everything in that document or get to the point where they can read it as they prefer. And so it's very common for users to go ahead and click that. After they do that, that document will now no longer be in protected view, and so then the prompt to enable the macro will come up, and that's that other yellow bar, which I have a picture of on the left side of the screen, and it will say security warning. This time it's a slightly scarier yellow exclamation mark shield, and it says macros have been disabled, and then there's a button for enable content. Now this one isn't as informative as to what macros can do, and so since it's so easy and it looks just like the other yellow prompt, what we find is most of the time users will go ahead and click that enable content button, not realizing that when they do that, they're now running malicious code on their system. And so the macro is an extremely common technique for initial access in a lot of intrusions by a lot of threat actors, and so that one is known, but the MHT variant of that is a little bit less common, and so that's why we see, that's one of the things that ties this campaign to previously reported activity. All right, after that point, the user has gone ahead and clicked that enable content button. What that does is that launches the macro. And so what does the macro do? Well, you can see a little excerpt of the code here. It's a little bit small. You don't need to worry about the details of that on the left there. But what it does is it uses the get object function to resolve through Microsoft COM a handle to WMI, which stands for Windows Management Instrumentation. And so once it has a WMI object, that enables it to make calls into this framework, which is built into every Windows version, which is called Windows Management Instrumentation. And WMI is a very extensive and very complex framework which enables you to do a lot of things, such as monitor for nearly any type of event happening on your system. You can do queries to see things like software that's installed, programs that are running, and in addition to all of and firmware and hardware, other information like that. But in addition to all of that, they also have methods which you can call, and one of those is in the Win32 process class, which they will go ahead and instantiate. You can call a method that will, the method is called create, that will go ahead and run whatever command that you want. So that's the technique that they use to launch a command. Now there is a much more direct way of doing that with a function called shell in the Visual Basic for Applications, which is the language that macros are written in. But these actors did not do that. They used this roundabout method to call it through WMI. And the reason they did that is when you call it through WMI, your Word document will then be making a remote method call to a different process, and then there will actually be a different process which launches that command. So there are some analysis tools and sandboxes that will simulate running your macros, but they won't see your macros directly creating a process. And so that avoids some of these signatures and detections, whether that's static, looking for that shell function, or dynamic and looking for that process creation. But again, this is something that they've been doing for a little while, so it's not unheard of, but it does still avoid certain detections. All right, so once they have then launched their command, let's take a look at what that command is. So it's a PowerShell command, which has arguments to run a hidden window, not loading a PowerShell profile, and then it runs the command that has a short bit of PowerShell that runs as a command. And that PowerShell then first is a very short bit of PowerShell to basically pull down the next stage. And so first it checks by looking at basically how many bits your processor is, whether it's a 32-bit or 64-bit processor, and then it will download the next stage, which is corresponding to your processor architecture. So it will then either pull down a 64-bit or a 32-bit next stage, and then execute it. And that one will again be PowerShell, but that one will be a loader for the next step of the malware execution. And that brings us to PowerSniff. So this next stage of code execution is running PowerShell, and what that will do is that has a small bit of PowerShell that will then extract out a binary rat into memory, and will do this without writing any file to the disk. It can also install that to the system registry, to the user's registry, where the next time the user logs in, it will go ahead and load up that PowerSniff rat as well. So now we're running with this PowerSniff rat in memory. So what's PowerSniff? Well, as we mentioned, this is kind of the latest and greatest version of this long line of Sniff malware. This version, launched from PowerShell, will run entirely in memory. PowerSniff is a basic rat or a downloader. Some people use the word downloader to describe a rat which has limited functionality but is used to launch other malicious code. And so what does that mean? It means it has capabilities for downloading other malicious files from a command and control node somewhere, and then saving those off to the disk and running them. This one also has the ability, which has been added relatively recently, to run that code in memory. And so it can also load additional in-memory modules without touching the disk. PowerSniff uses standard HTTP or HTTPS. These are normal web requests for communication. And when it does that, it calls back to a known URL format. Now, this format has undergone some changes, but the overall structure and the overall parameters mostly stay the same. And so there will be this query string, which will have different parameters in it, like ID, var, OS, OS2, host, K, and type. And these will be derived. We won't go into the details of what every single one of these URL parameters are, but basically they'll all have system information about what operating system you're running on. There will be a hash, basically, to uniquely identify this particular system and what type of system it is. And then that will all go back to their command and control node. Now, to my knowledge, I haven't seen anyone obtain a copy of the actual control software, but presumably this is written in some web server language like PHP, and then taking all of this data in, dropping it into a database, and then returning back commands, which the operators have then provided to this particular system. Once again, PowerSniff can be installed in the registry, so we did see that happen, and we saw when PowerSniff is running, the commands that come back all have different codes, and you can see some of the commands listed there. They're all basically decimal text. So they're all ASCII text commands, like 111, 222, 333, all the way up to 922. And each of those commands corresponds to something different, like drop a executable file and run it, or drop a DLL and run it, or run a blob of shell code into memory. And those commands are going to be coming back most likely encrypted. One of the unique functionalities that we saw our PoSlurp variant perform that we hadn't seen openly analyzed before was the ability to drop a DLL and install it persistently in the system under a key known as the AppCert DLLs. And so this is a not commonly known technique to persist on a system. So again, it can avoid a lot of common detections out there. And those DLLs which are registered in that registry value will get loaded and executed anytime a new process is created. And so another characteristic of PoSlurp is that when you take a memory snapshot, you can find a lot of the plain text strings in memory. So for example, and here on the left you can see a snapshot of what that looks like loaded into memory. And so you can see there's, if you look closely, if you can't see it, don't worry about it, but if you look closely, you can see the URL pattern, you can see the different commands like 444, 333, 666. You can see some HTTP verbs and some various paths which are used and all that kind of stuff in memory. And so these are things that you can use to get signatures. You can scan the memory with Yara and that kind of stuff. And so it's relatively easy to identify PoSlurp and some of the other Sniff variants using those strings. All right, moving on, the PoSlurp loader did incorporate function hashing code that we recognized from the CarberP Trojan. Now, the CarberP was a different malware family, and that source was leaked a few years ago, but it is interesting that they went ahead and pulled that in for just that one function. Other behavior that we saw was injection into explorer.exe. We also noticed that it did not have a way to deallocate its own memory at exit. So even if they have attempted to turn off this PoSlurp module, as long as those processes are still running and that computer has not been turned off, you would be able to find it in memory. The variant that we saw had significantly improved sandbox detection methods over what has previously been openly analyzed. Things like obtaining the hard disk volume name, taking a checksum of that, and testing whether or not it matches, or looking for system firmware information, or running through a process name hash blacklist. So that's a very interesting technique to quickly detect a wide range of analysis processes running that they then, if they see that they are running on a sandbox or a researcher's system with all these analysis processes, they're going to quick exit and not risk revealing any of their further techniques. Another thing that we saw was that previous variants have long been reported to have various strings and capabilities in them to attempt to detect if they're running in a medical, like hospital or school environment, and to exit if that's the case. And what we saw is those have now been removed. We can't say for, I can't look into the mind of the actors behind this, and I can't say for sure whether that's because now they're okay with targeting those, or if they believe that their targeted access methods, which is spear phishing, they know who they're sending it to, they know it's not going to accidentally end up in a hospital or school. Either of those might be plausible options for that. And then again, we have the standard functionality, such as running a DLL exe or loading the DLL with load library W directly into the same process that it's in. All right, and that brings us to the new. So what did we see here throughout this campaign, which is different than what we've seen before? And that was the biggest piece might be the ShellTea rat. And so ShellTea looks like an overhauled rat from the same people who wrote PoSlurp with a lot of changes. So first of all, it's not using HTTP or HTTPS like the Sniff and PoSlurp did, which was one of the biggest, and most consistent indicators of Sniff and PoSlurp. So ShellTea now loads its own custom binary protocol. It doesn't even load or use the Win INET network libraries, which the other variants call to do their communication. As a result, of course, you now will not see any of the query parameters because, again, it's not doing communications in the same way that the PowerSniff people are. Another difference between the two is the command structure. They're no longer using, I should say, ShellTea. ShellTea does not use ASCII repeated decimals like we saw text strings like 111, 222, 333. Instead, each of the commands that ShellTea takes are sequential binary integers. So now they're working on the raw bytes instead of the text strings, and they're not using the same numbers either. So it's got a different set of commands. It also has a different API calling method. So this is significantly advanced over the method that PowerSniff has used because it's doing hash resolution for every function call on the fly. So the way nearly every other memory resident malware works is it will load itself up, load up basically some type of DLL in memory, hook up all the imports for all the functions that it wants to call, and then launch that. A malware reverse engineer can then go look at that malware in memory, pull off all of those functions which have now been resolved, and see immediately what they are. Well, with ShellTea, ShellTea is in a minority of memory resident malware, which will do the hash resolution on the fly. And that function address which they detect every time they want to call a Windows function, so these are things like write a file or launch a process or connect back over the network. All of these different functions will be resolved on the fly, and that address will remain in the CPU register. It will never even be saved in memory. And so this enables them to avoid that style of analysis very easily. The other thing is that they have managed to eliminate all of their plain text strings in memory. So again, this is significantly advanced over what you see in the Sniff family. And we do also see an improvement in capabilities as well. Although they have many of the same capabilities, there's built-in methods now to launch PowerShell script execution, showing that the actors are moving to really a PowerShell-centric modus operandi instead of the binary and standard commands that you saw earlier. And we also see an overhauled sandbox detection again, removing some of the detections which were in PowerSniff and using different algorithm and a different number of analysis processes detected. Now we did see a similar bug in the same library, the same mechanisms in ShellTea as in PowerSniff, despite all the changes. So again, we still do believe it is the same actor behind it, but there's been so many changes that it's no longer looking like Sniff at all in memory or on the network or in nearly anything that it does. And so that really merits the new name of ShellTea. And finally, one of the advancements that we've seen is that it now can perform in-memory cleanup when they are done using a rat. They can tell it to unload, and it will erase its own memory, which is a really neat routine because this is something which is not commonly known. I certainly haven't seen it in any other malware in the wild. There's one or two places that I was able to find it discussed in forums online, but again, not commonly used. And so this one is, it's very clever. What it does is basically overwrites the return address on the stack with RTL exit user thread, or the address of that function, and then it jumps to a function called virtual free. And this is the function that Microsoft Windows uses to deallocate memory. So it calls virtual free to deallocate its own memory, which is then cleared out of RAM, and then it returns, instead of back to itself the way it would in a normal function call. Since it no longer exists, it now returns directly into this Windows library function RTL exit user thread, which does what you might guess from the name and exits that thread. When it exits the thread exit procedure then deallocates the stack, and so even that piece of memory is now cleaned up. And so this removes nearly every trace of ShellTea from memory, which is, again, quite an advancement. Other aspects of ShellTea that you might see are reading proxy data from the registry. Again, since it's no longer using the built-in Windows library functions to communicate over the network, like PowerSniff does, ShellTea has to read the proxy data directly and decode that, and it can communicate through proxies as well. It does use the XT encryption algorithm in CVC mode, This was something that other samples have used. And then again, we mentioned the improved sandbox detection. All right, so now that the adversaries have access with ShellTea, what they want to do is go get their main target, and that is the point-of-sale systems. And so to do that, they're using a piece of malware that we call PoSlurp. PoSlurp is a highly obfuscated RAM scraper, and that they deploy to point-of-sale systems. Uses a 3-step loading process with multiple layers of obfuscation. This one, in contrast with the other samples that we've been talking about, does start as an executable file. And that obfuscated, highly obfuscated executable extracts out the next stage into memory. And so that uses a technique where they access a function called RTL write memory stream, which is a function which is present in Windows but has never been implemented. And what they use is they use the unimplemented error code as a constant to then create the next function API hash, basically the next number to find the next function they want to call. And so this, again, is a really interesting technique I haven't seen anyone else describe or use before. After that, they use those functions to extract out the second layer into memory. And this in-memory stage uses the carb-p function hashing algorithm again. As we mentioned before, that is a publicly available function hashing algorithm to then extract out, load up, and link up the final inner embedded stage 3 DLL. And so this one looks more like a compiled piece of code, which is then loaded into memory. This third layer is where all the business logic of PoSlurp happens. So what this does is it parses the command line of the calling process, and there are 3 main elements of this command line. The first element is going to be the process names that PoSlurp is going to monitor. So it will read out each of those and store it in memory. The second element of that command line is the duration to run collection. And so in minutes, basically how long they want to keep recording credit card numbers. Now you might ask yourself, why would they program it in to exit after a set amount of time? And we'll get into that in a bit. But basically they don't want to overload themselves. And so what they'll do is they'll run it for a short period of time, like a day, grab the credit cards that have been stolen, then kick it off again. After they have gone ahead and ran that, it will look at the third argument in that command line, which is a process to inject into. So you can specify, hey, I want to inject into this process, and then process A, and then monitor processes B and C for this duration of time. And so it will then do that injection, copy over the configuration block into that process, and then exit the original process. So that original process will only be in existence for a split second, and then it will be gone. The malware will be running in memory. So after that injection, it will be running its RAM scraper routine, and every 5 seconds it will scan the memory of the processes that it has been instructed to scan. And so it will only scan those processes' memory, and it will look for patterns of data indicative of credit card data. Once it gets those, it finds one of those, it will then check, it will compute basically a checksum of that credit card data and add it to its list of known checksums that it has collected. And if it's already in there, then it will say, oh, not adding that one, not outputting that one. So this is a duplicate check that it uses to avoid resending credit card data that it's already collected. And that duplicate check, there's space for about, if I remember correctly, 10,000 different unique credit cards that it can collect. And every time it sees a new credit card come in, does that hash, does that check, it has to scan over the entire list of duplicates. And then once it hits the end, that list can roll over, and you can then start collecting more. So that's one of the things that starts to get just ever so slightly slower the longer that it runs and the more data that it collects. All right, and so with that, we've gone just slightly later than we intended. Are there any questions that the audience has?
And if there are any follow-on questions, you can contact us via info@root9b, and we'll be happy to get back to you. This is the end of the webinar. Thank you all for attending.